last day. So we're going to have 3 talks in the morning, and then we've got a couple talks and 1 student panel in the afternoon, and we'll be closing off the workshop. You've been great at participating, and I encourage you to continue to do that for the remainder of the day today. So to get us started today, I have the pleasure of having now Dr. James Halverson kick us off on a topic that is going to be very important. James was a PhD student working with me over the last few years now, and he has done a lot of work on machine learning and AI in cybersecurity applications, and done some of the things that are so critical in terms of getting data, sometimes synthetically generating them. He has worked on intrusion detection systems, things that the power grid needs, and supporting some of those applications. And he has developed a set of tools that are also important in terms of coming up with good metrics for sensors and other things in networks. And so his specialty is in intrusion detection systems, but I think he will take a little bit of broader view and talk to us about applications and challenges in AI in cybersecurity. He has just finished his PhD this spring and is now not in Pullman, and that's why he's joining us over Zoom. James, thank you very much for taking the time. The floor is yours. You can save some time towards the end for Q&A.
Sure.
And take it away. Thank you.
All right. Thank you, Asifa. Um, Now, a few years back, I actually presented a talk here on machine learning in cybersecurity. And in some ways, this is actually going to be a continuation of that um, with a more broader view on artificial intelligence here within cybersecurity. Um, Now, I'd like to start off by talking about who I'd like this talk before, and ideally it's everyone here. But especially I want to focus on students who have perhaps an interest in artificial intelligence or machine learning, um, so that they can get a good idea of what exactly it is the technology that they will be working with when they uh, merge their interests in cybersecurity with artificial intelligence and what sorts of challenges they're going to be dealing with. I also want to be of benefit to any security professionals who may be in the audience who want to learn a bit more about what technologies there are in the field. I will not require anybody here to have prior knowledge about artificial intelligence, but I hope by the end of this that all of you will learn a little bit more about what tools there are available. Um, so here's a question for everyone. What exactly is artificial intelligence? Because even though a lot of us have been working with AI tools on a day-to-day basis, with all of the new LLMs coming out like ChatGPT or Claude, um, there's still sometimes a little bit of confusion around the definition. Um, so in many cases, we might see people asking, well, is it real artificial intelligence? And they come from this perspective from viewing science fiction that artificial intelligence is going to look like some sort of super intelligence like you might see in the Terminator or whatever. But in actuality, it's a bit more of a broad definition. This guy here that we see on my slide is John McCarthy. He is the uh, father of artificial intelligence and also of the Lisp programming language, and he defined it quite elegantly as the science and engineering of making intelligent machines, which seems a bit vague, although it's been refined a bit to the science of making machines do things that would require intelligence if done by humans. Um, our modern AI technologies will often incorporate elements of machine learning, though they're not defined by it. So, for instance, Stockfish, which is a chess AI, used to not even use machine learning, but instead use a search algorithm to sort of choose the best chess move. And that is still AI. So all machine learning is AI, but not all AI is machine learning. Um, and while there is a push right now to try and create artificial general intelligence, um, where we're trying to make AI that is good at many things, like a human, it's not necessarily something we need when we work with AI in cybersecurity. We can work with more narrowly tailored AI. So, what are the main areas that AI is being used in cybersecurity? Well, we can broadly break this down into some of the defensive applications and offensive applications. And this is not an exhaustive list, but it is where I am seeing most of the work. For defensive applications, we of course have intrusion detection, where we're trying to monitor some network or host behavior, and every time we see a threat, we raise an alarm so that someone can do something about that. And that gets taken a step further in intrusion prevention systems or incident response systems that will try and take some sort of automated action against the threats that we see from this monitoring data. Um, for offensive applications, we have tasks like automated red teaming. So we're trying to uh, construct some sort of cyber attack test against our network. And so the AI is going to be tasked with planning the series of um, attacks against it. Um, we also have vulnerability analysis, where we might take a look at some computer program and its source code or its binaries and try and detect vulnerabilities within it. So, why even talk about AI in cybersecurity? And the answer is that it's sort of a numbers game that we have to deal with. We have a ton of different places that are becoming viable targets for attackers. We've seen hospitals being targeted by ransomware. We've seen power infrastructure that might get targeted by foreign governments as an act of warfare. And of course, our own government infrastructure is also a valid target. Um, and for every single one of these computer networks, we can't have a human that is going to be the sole defense of it. Even if we were extremely prolific at training everyone on Earth as cybersecurity, uh, these people cannot be everywhere at once, and we have to take to sleep, to take breaks, etc. Um, and AI has the potential to defend any network 24/7. And the question we might want to ask here is, should we have an AI run 24/7 defending our networks? And this, I think, I would like to have a discussion about at the end of this presentation, because it is an interesting question. Now, before getting into depth on the different types of artificial intelligence that you'll encounter within the um, cybersecurity task, I'd like to give a brief introduction on machine learning, because this will give us some context about how each of these AI algorithms are working in each of these applications, and sort of introduce some of the terminology. Now, machine learning, which we've already discussed, is, part of AI, but not all AI is machine learning. I define machine learning as a collection of techniques that enable a machine to learn the definition of a function. So we're going from some set of data to producing some sort of mathematical function. And the input for this function typically is what we call a feature vector. So for anybody here who is a programmer, think of this like a fixed size array of IEEE floating point numbers. That is typically what you're going to be working with. And the output of that function is going to depend heavily on the task. We typically break machine learning down into three types of approaches, one of which is called supervised machine learning. So our training data is having some sort of labels, right? So we have feature vector next to an output already provided in the data set. And that can be either classification, where the label is going to be some sort of category, or it can be regression, where it's some numeric value. Um, as an example of supervised machine learning, we have the neural network, which is what I have depicted here in the top right. That is one type of supervised model, although there are also variants that are used for unsupervised and reinforcement learning. And that can be described like a bunch of these hidden layers stacked together. And each one consists of weights, where you're multiplying values from its input by the weight, and an activation function um, that is applied after uh, all of these um, input multiplies are aggregated together. Um, so you can think of it as a repeated application of some handful of functions. Next, we have unsupervised learning, where the goal is to find some sort of a pattern in unlabeled data. We don't have the um, output for it, but we can try and cluster that. So as an example, I provide k-means clustering, which I've shown here in the lower right corner. Um, you see here a bunch of dots in some uh, vector space, right? Um, and we're trying to figure out, well, how would we categorize each of these dots? And so um, the method used in k-means clustering is to move every one of these points to a central position until none of them change their class. Um, so the right part of this figure shows how they inevitably end up being um, clustered together after picking some arbitrary number of classes, say 3. Finally, we have reinforcement learning, where the goal is to learn a policy. So that is basically some sort of strategy for an intelligent agent. It tells it how it should act given certain inputs. And that's your crash course for machine learning. Next, should talk about our first application of artificial intelligence, um, which is intrusion detection. Now, an intrusion detection system is tasked with monitoring the activity on some network or some host and raising a alert every time there is a threat. Um, there are several different types of intrusion detection systems. We can consider them as signature-based versus anomaly-based. Signature-based are going to um, say, does this data match something within our database? And anomaly-based is going to say, does this look different from data that is typical for this system? We have host-based versus network-based intrusion detection systems. So are we trying to focus on, say, the behavior on the device, or the behavior that's going between devices on our networks? Um, and then we have rule-based intrusion detection systems, like expert systems, versus statistical approaches um, that might try and go based on patterns of typical behavior. Now, an intrusion detection system, its main goal is going to be raising alerts, and that's pretty much all they do. And when this response, or when this alert is, um, when we have some sort of uh, automated response, then this is what's called an intrusion prevention system. Now, intrusion detection systems are very heavily dependent on uh, data, and that's worth talking about in a little bit more detail. The type of data that they're going to collect is going to depend on the type of the IDS. If we have a network-based intrusion detection system, we're going to be focusing on things like net flows, which is our summary of the packets that we receive. This figure here at the left is an example of net flows. So we have the protocols, the number of packets, the source IP, but we don't tell what's in the packet. Um, Another type of data for that is packet captures that are more focused on what were the exact bytes that we sent. So we might be able to do deep packet analysis. A host-based IDS is going to focus on a much more varied set of data. So it might consider incoming and outgoing packets, but it's also going to consider things like uh, what sort of behavior occurred on the file system, what sort of processes were created or terminated, and whatnot. Um, so we have a wide variety of data that we might have to consider here. And did my... Okay, there we go. Thought my computer froze for a second. Um, anyways, um, this data that we're having to deal with in intrusion detection systems is often highly categorical. So we have to deal with features like file names, IP addresses, um, alert IDs, and whatnot. Um, and sometimes we have nominal values like the number of packets or whatnot. But because of that, we have to um, find methods of encoding that data um, that might be different from other types of machine learning tasks. Um, for instance, if we have an off by one error, um, what that might mean is that we have a completely different value instead of a slightly different value. Um, Compared to the task of, say, um, dealing with image data, where off by one means that your red becomes a slight orange or a pink. That's not too much different, where here, uh, a off by one with an IP address is, you know, a completely different computer on the network, or potentially even a computer halfway across the world. We also have to deal with irregular structures in intrusion detection. So, for instance, function call graphs or time series data. Um, the figure at the bottom left here is a function call graph. And if you can think of how you might want to transform that into a feature vector, which are like a continuous array of floats, um, you can see that would be sort of a difficult task. Anyways, so what types of AI tools do we have in our in intrusion detection? Um, well, since most of it is focused on anomaly-based detection, we will often have um, unsupervised machine learning approaches. So we'll try and learn the function of mapping the event to either label of benign anomaly, and because we know the number of classes ahead of time, we might use some sort of clustering. Although we also have dedicated anomaly detection algorithms, such as the isolation forest or the one class SVM. If we do use supervised approaches, we have a need for um, labeled data that is mixed and that isn't always easy to come across. But we do have at least some high quality algorithms. I've found that deep neural networks can be very highly performant when you give them the right quality data. And regardless of the approach that you use for intrusion detection, um, it should be noted that it's not always something that you can uh, train a model on some uh, data set and then just ship it to um, an end user because the IDS does need to know what is normal for the end user's network, not just for any network. Some of the challenges we have in intrusion detection are that there isn't a lot of labeled data available, and the data that we do have needs to be uh, pre-processed in a lot of different ways, depending upon um, what type it is, since we already have a varied uh, group of data. Another is that we often have to deal with false positives. Um, and when we get a false positive, it can lead to an incorrect response if we're, say, um, using an intrusion prevention system. Um, and if not, and we get too many false alerts, then the human whose job it is to act upon this intrusion detection system may start to ignore these alerts, and so it's as if we're not using anything at all. Then, for signature-based intrusion detection systems, we also have the problem of zero-day attacks. So if we are trained only on certain types of data, then anything out of the data set becomes a problem. Anomaly-based intrusion detection systems are able to deal with zero-day attacks, um, but they're still a little bit imperfect. Um, and if our attacker is in possession of the classifier model that we have, then they can always uh, craft an attack to evade it. And in fact, there's some research to show that even if you don't have access to that model, you can distill the model from providing certain responses um, or from providing certain actions and seeing how it responds to them. Um, So that is some things to consider with how to improve intrusion detection systems. Next, we've got incident response or the intrusion prevention system. Our task looks like this. We've received an alert from an intrusion detection system, so we know that someone's attacking. Now we need to figure out what can we do to that. And so that requires a little bit of triage. First, who rose the alert? How did they trigger it? Um, what are they trying to do within our network? Trying to determine the attacker's goals can figure out what's the best strategy here, and what action, if taken, would prevent them from achieving their goals. And from that, we need to figure out an appropriate response. And our responses can look like blocking network connections between various hosts, or it might be preventing certain scripts from executing, terminating a process that might be compromised. Well, for artificial intelligence use here, this is not as well researched as intrusion detection, but they're often a hand-in-hand um, thing because intrusion detection is the first half of intrusion prevention, the other's figuring out what to do. Most research is focused on helping humans to respond to things. Um, for instance, making suggestions at how we might respond, but not actually doing an automated solution. But hypothetically speaking, we could have a fully automated response. Assuming we had intrusion detection system that never gives a false positive, we could train a classifier on some number of attack scenarios um, and figure out what would be the best response to that. Um, and the machine would take that response without needing human input. Um, Now, for some offensive security applications for artificial intelligence. Red teaming. Um, so red teaming is when we're trying to test the defensive capabilities of our network. So we're going to simulate some sort of cyber attack. We do this with a red team and a blue team. The red team will typically be given some goal to access, say, sensitive information and use whatever. means, excuse me, whatever means they have necessary. And the blue team is not necessarily going to be told that this is an exercise. They're going to be the um, cyber experts that we have, and their goal is to prevent the attackers. Um, this is going to require um, a fair amount of human experts that are trained in cybersecurity, and that's going to cost a fair amount. So the question then becomes, can we automate this um, so that we don't have to hire offensive security experts? Um, and automating that is an instance of the AI planning problem. So planning problems look like we have an initial state, a goal state, and a list of actions we can take to go from one state to another. And so we want to find the sequence of actions that gets us to the goal state from our initial state. And our actions in this planning problem will have their preconditions. So that is what must be true before that action can be taken. We have effects, so what is going to be added, deleted, modified, etc. And they're going to have costs. Finally, the other offensive security application for AI is in vulnerability analysis. So software vulnerabilities are any bug within a program that has a potential to become a security problem. And vulnerability analysis outside AI has a handful of different high-level approaches. We have static application security testing, where we are inspecting our code without actually executing it. So that might look like just straight up reading the code base and trying to find certain um, vulnerabilities within it. We have dynamic application security testing, which is where we are uh, inspecting that code at runtime, trying to see what uh, odd behaviors might occur from its execution. We have interactive application security testing that combines elements of both the static and dynamic analysis. We have fuzzing, which is input-based security testing. So we're going to throw a bunch of um, completely bogus inputs at it to see how it responds to that. We have pen testing, where we have simulated attacks in order to evaluate security, and we have formal verification, which is trying to use mathematical proofs to figure out is this program correct. Now, in vulnerability analysis, we have seen uh, a lot of use of large language models recently. Large language models are AI that's trained on text prediction. So this is your OpenAI, your Gemini, your Claude, etc. And they've been, trained on source code recently, not just natural language. So say we prompt an LLM to say, um, find a vulnerability in this code base. Doing this is going to require a very large context window, um, depending upon the size of the code base. And so that's going to increase the number of tokens that you need, which is going to increase your cost. Um, and the accuracy of doing this currently is roughly 50-50. It's not great, but it's getting better. With that said, the data sets we have for vulnerability analysis are skewed towards certain vulnerabilities. So, for instance, you might be very good at detecting buffer overflows or injection attacks, but you might not be very good at detecting um, vulnerabilities related to concurrency because they're currently not available in the data sets. Um, there have been some very old vulnerabilities that have been found thus far. So, for instance, in the FFmpeg um, H.264 parser. We found a um, out of bounds memory access using Claude that would be able to be exploited, um, I believe, for some arbitrary code execution, as well as a signed integer overflow bug that was 27 years old in the OpenBSD TCP implementation, where uh, it was possible to overflow the value of a pointer um, to cause a null pointer exception and crash the operating system. Um, we're seeing rapid improvements um, in this vulnerability analysis task, but strictly speaking, it is still an undecidable problem because, as we may know from a class on computability, um, any Turing machine can't tell what the behavior of another Turing machine is. It's just a matter of how big of a context window can we use. Um, so how much does this matter? It's going to be a question of how much can you spend on tokens? How much memory do you have to analyze your code bases long term? Okay, time for a few case studies. Um, one of which is related to the uh, automated red teaming task, I believe. Um, so this was privilege escalation with reinforcement learning. And in this case study, we had a simulated Windows machine that would have, let's see here, a
Can you get that pen out of the way, James, if you can? I was going
what?
to get the one that they're moving around now.
Yeah.
Can you get it out of the way from the slide?
Ah, yes, I can try. Yeah, I was not aware if that was showing up on your end.
Yeah, it
Um,
is. Can you minimize it?
let's see here.
Yeah,
That's how
that's
far I can minimize it.
yeah, that's much better. Yeah. Thanks.
All right. Thank you. So this was an example of using reinforcement learning in order to accomplish that automated red teaming task. So we gave um, a Windows machine that had some random selection of vulnerabilities, and we gave our uh, AI agent 38 different actions that it could take. For instance, overriding DLLs, testing certain credentials and whatnot, and use this actor advantage critic method to learn its policy. And the result of this experiment was that we were able to find many different ways of accomplishing the privilege escalation task, many of which were able to avoid detection by antiviruses. Um, so what this means is that our reinforcement learning agents are able to produce flexible attacks that can adapt to our environment and might be able to exploit unknown vulnerabilities in the future. All right. And another case study. This is actually in the last couple of months, which is the Claude Mythos breakout. So Claude Mythos is a preview version of the Claude large language model that's not currently available to the general public, and it is also not explicitly trained for cybersecurity tasks. It is just really good at code generation. And what we had was that um, Claude was placed in a secure sandbox environment, so shouldn't have access to the network. And it was told, go escape from your environment and send me an email. And what it does is it executes a multi-step exploit on the environment in which it is um, found in. That's not knowing exploits, that is just knowing code and also having um, some level of reinforcement learning to make it a AI planning problem. Um, and as a result, it was able to obtain internet access and sent an email to the prompter when he was sitting in the park eating his lunch. So the takeaway from this is that having cybersecurity knowledge and being able to detect vulnerabilities and whatnot is an emergent property of being able to work with code generally for large language models. And there are some AI safety concerns as a result of that, um, which leads me into my discussion questions. Um, and in fact, from that, I'm going to bring up my uh, last discussion question first, which is, do the benefits of AI usage outweigh its risks and limitations, and what risks are there to using AI to defend a network? Um, so if Claude is able to exploit vulnerabilities within your network, then it's not a question of uh, is this capable of improving our security? It's a question of, is that AI aligned enough that it does not become a threat to our security? Because, we have a hacker as our defender. Um, and one last discussion question I'd like to consider is, what other ways might AI be used to improve cybersecurity? I've discussed four main tasks, but I'm interested in hearing from the audience if you think um, there might be some better ways we can make use of this technology that we have. So I open the floor for any questions or for any comments on these discussion questions.
Thank you very much, James. We can clap, I think. Uh, but there are, some very interesting discussion questions that James has brought up. You could either comment on them or ask questions if you have to James. And I'm sure to be passing around this one if you guys have questions. You got one? Okay.
You mentioned Mythos in your presentation, and I just wanted to ask your opinion. How much of Mythos do you think is revolutionary versus marketing and hype?
Um, I'd say a lot of the features that are currently in Mythos are very likely within other large language models. Um, but I don't think I've seen uh, other large language models currently able to uh, engage in this type of exploits. So in this case, it might be just a little bit farther ahead. Um, but I mean, I don't have access to um, anything classified or any um, currently hidden from the public information about models like Gemini or ChatGPT. So it's possible that the others, might have this capability as well. They're just not willing to share it.
Thank you.
All right.
Just out of curiosity, do you know how long it took for this Claude Mythos model to break free of this sandbox environment?
I think it was like a couple of hours. Um, but I have not looked into the exact time frame of how that occurred.
Hi, James. I actually just had a question about like earlier what you were talking about with the host-based IDSs and network-based IDSs.
Yes.
Like with using AI to help like implement those with like using like anomaly detection in the forest that you talked about. Which is more difficult to implement, like a host-based system or the network-based system?
Um, I would say probably host-based. I see a lot more research on network-based intrusion detection systems, and um, there is uh, not as great a diversity in the types of data. Um, but host-based data or intrusion detection systems, we have to deal with things like malware and whatnot. And so the task of figuring out if some binary image is an example of malware, um, that comes down to the same decidability problem that we've got for vulnerability analysis, except instead of trying to determine of can this be exploited, it's will this do something bad? Um, and what I've seen for host-based intrusion detection systems that are dealing with malware often is a question of does it invoke these APIs and whatnot? Um, and sometimes, that can work, but uh, if it were just a matter of figuring out what APIs it would use, right, you could just shut down those APIs, except they're also needed to be used for legitimate applications. So um, it's kind of a hard problem.
All right, thank you.
All right.
Other questions?
Any further questions?
There are coming.
Hi, James. It's James here.
All right.
I was wondering, going back to the Claude example, has anyone done anything sort of along the lines of a similar to a generative adversarial network where, instead of putting two neural networks head to head, maybe putting two versions of Claude head to head and telling, one to be an attacker and one to be a defender and just sort of train them off each other and see kind of who wins or something like that?
I don't think I've seen that task done before, but that would be a very interesting experiment to run. Um, you could use that both as an automated red teaming and as an automated blue teaming example. And if you conducted, say, um, several experiments, you might be able to um, get a sense of is AI better at the red teaming task or the blue teaming task?
Yeah.
So that would be a fun experiment, but I haven't seen it done yet.
Okay. Thanks.
So I have a question for you, James.
Sure.
You can put up the ones that you had this discussion questions slide up. You did mention like a number of different ways in which AI could be used, and you are asking about, what other ways can be there. And I
Yeah,
know there's
I'm
something
just
that, and I know there's something that you have worked on that I think would be relevant to bring up here. So when you work with machine learning,
yes, I have been
for
working.
whatever it is, you would need data, and there are applications where you don't have shortage of them.
Yes,
You've got
I have
plenty
been
of
working with generative models to solve the intrusion detection data problem.
yeah. Can you
Also,
comment a little bit on that?
yes. Um, so for those uh, who are not deeply familiar, the uh, data problem in intrusion detection is somewhat solvable through generative models, um, although it does introduce its own extra levels of difficulty. So the idea is that we have, um, say, some large data set of maybe net flows or process logs or whatnot, and each one of those is labeled with some different type of an attack. And naturally, we're going to find that certain attacks are overrepresented and certain attacks are underrepresented. And the benign classes almost certainly going to be the most overrepresented class. And with generative models, we can take the underrepresented classes, we can resample them and create new versions of that data. I haven't really focused that within my slides because I consider that all to be part of the intrusion detection problem in general. But that is one way in which AI could be used for improving that problem. That said, there are some caveats. I had mentioned um, this off by one error when you have uh, mapping of category labels to floating point values, and that is um, most prominent when you are dealing with generative models, because generative models start from a source of randomness. You take that randomness, put it through a neural network or some other uh, type of model, and it comes out as a feature vector. And if you get an off by one on the feature vector, you've got a completely different class. So you need to have that encoding strategy down very solidly.
Mhm. All right. Thank you very much for that, James. I think we will wrap up here and we will have a short break before our next talk. Thank you again, James, for a great talk on an overview here.
All right. Thank you.
Yeah. All right.